13 millions to the estimated slag production will be about 24 million tons, which will be significant. But there is a problem here. I don't know how long we can continue with this kind of a steel production for sustainability again. But as long as it is there, this is a wonderful material, probably the best mineral admixture which you can get for incorporation in concrete. No questions asked, because Germans have shown that almost 100 years back that slag can be used in cement. Something alumina industry gives us about 9 to 10 million tons of red mud and quite a bit of wollastonite mineral admixture, but may not be very active in terms of reaction, but definitely can replace the sand part, which we are also struggling to get going in this country, so that can participate there. Why does these things interest us, basically? The simple thing is, if you look at the cement clinker and the basic oxide compositions, generally they are all calcium oxide, silica, alumina, iron oxide, and few other minerals, let us say. In cement, predominantly it is calcium oxide and a little bit of silica to form what is known as calcium silicate hydrate, and then calcium aluminate hydrate. Now, the other materials, whatever I have suggested in the previous slide, if you take them, they do have similar product. But calcium oxide is less in fly ash, which is called low calcium fly ash. But GGBS gives us almost 50% of that calcium oxide and about similar silica. And hence GGBS is also sometimes referred as cementitious material. Okay, supplementary cementitious material. Whereas the other material which I talk about, wherein predominantly silica, almost 50 to 60% of silica, no calcium at all, not much, significant amount of alumina and some amount of iron oxide, can be regarded as pozzolana, wherein on their own they do not react, but in the presence of calcium hydroxide, which is the byproduct of a cement hydration process, they again react to form what is known as calcium silicate hydrate, and the hydration can happen. Now, this was a kind of a magic about 15-20 years back. People started realizing the importance of such materials. Only thing is whether those materials are good enough to be used, because they are byproduct. Nobody manufactures them, but in its as collected state, whether they can be used or how much minimal processing is required, took us quite a bit of time for incorporation, and of course little mental blockage of using such materials was one of the issues which we did. But people realize that particularly fly ash, let us say, which is available abundantly, had a wonderful morphology, nice ball bearing kind of a spherical particles, which contributed more towards workability and quick reaction. The interest I showed, C3S or C2S maybe, when reacts with water, sorry, this is not CH, it is H. When reacts, it forms what is known as calcium silicate hydrate, which is our insoluble strength giving component, and then calcium hydroxide. That's depicted here. When your cement particles along with water, this blue color, reacts, you get what is known as calcium silicate hydrate, this dendritic structure between, and quite a bit of calcium hydroxide goes initially. This calcium hydroxide can again come in contact with the silica, which generally is encountered in most of these byproducts which you choose. Or in fact, if you're choosing, you should choose wisely with more of silica, react to alumina, and react to iron oxide. And then start producing more and more strength-giving calcium silicate hydrate, insoluble, and get it more and more dense. This was the magic which used to happen, and people realized that it is very important to look at them very closely. And there were many other advantages. Increased strength came, increased durability came, strength and both compressive and tensile strength consistently people reported over a period of time, extensive research throughout the world as a result. And then because they were finer material than the cement used, less than 20 micron, the average size of the cement is about 20 micron. They also introduced more and more cohesion to the mix, and the bleeding, settlement cracks in the initial. So some of the things which were inherent problem for concreting in 70s and 80s started disappearing once we started using small amount of these materials, 20, 30, just as a replacement. More importantly, which is very important, let us say if these two are calcium silicate hydrates, they are actually dendritic structures like that. And in between these secondary reactions used to go and block those capillary pores. Now, capillary pores are generally considered as the flaws in a concrete. And if you can plug them, you are actually making it more durable. Of course, strength will improve. Any void is filled, strength will improve. More importantly, durability will also improve. And that was fantastic, proved beyond doubt. And worldwide, people started believing in them and started using them. So this is first step towards sustainability in terms of reduce. So fly ash, GGBS, ultrafine, SEMs means you start grinding them. And then, of course, now people have moved towards composite cement. Cements themselves can use combination of fly ash, etc. One can use it to get those carbon credits, in fact. But the start was slow, as you know, because IS code or any other code wanted to go a little slow and restricted the amount of use for various reasons. So it stands at about 35% here in India. GGBS, of course, because of its cementitious properties also, can be used up to 70%. 50 to 60 is very easily can be done. Whereas British and American standards were a little more liberal, and they went about 55% in British. Americans restricted 35 minimally, and then they moved on to much higher percentages. So the framework came as early as in 1996 in British standard, and then after 5 years we followed, and ACI has been using it quite significantly, even early 90s, if I remember correctly. So there is a move, and composite cement is work in progress. They was already coming to market. Probably Manjunath might have already told yesterday that their company is coming out with composite cement. By name composite cement itself. Though there is an IS code, composite cement way back and modified in 2015, nobody used to produce composite cement because the type of pozzolanas available at that point of time were not simply good enough to get a good cement. The brickbat powder, etc., people tried, but they were not successful at that point of time. Okay, so this is what happened, and then quite a bit of work is happened from that point onwards. So as you see, we started with Portland cement. We started using pozzolana cement, 10, 15, 20% of fly ash, and now available freely. They call it as pozzolana cement. Most of it, in fact, most cement companies have set targets to them that they will reduce selling OPC unless it is required for special purpose. OPC will be also a history. Only clinker cement will be history. There will always be blended cement, blending with fly ash, blending with GGBS, blending with any other material possible. Quite a bit of work is happening on that. Then came blending with concrete system, direct blending. I take OPC, but add directly how much I want, but then they have to be engineered work. An engineer in charge, a concrete engineer particularly should be there. About 10 to 20% generally happened every early 90s. Then came the concept of high volume concrete. Canadian Professor V.M. Malhotra and P.K. Mehta and so many people came together and did fantastic CanMet conferences in early late 90s and early 2000 and promoted what is known as high volume fly ash. Volume means basically when we calculate absolute volume, 50 to 60% of fly ash as a replacement can be used by volume. Okay, so that was something which was very radical at that point of time, and people did not believe that whether I can go to that level, because they were very happy with only that. But gives significant credits, basically. Carbon credits can reduce significantly. So something, an example of high volume fly ash concrete is if I am using a binder cement, typically, let us say about 430 or 435 kgs, look at the amount of cement I use, only half of that, 40, 50, 60 on an average, 50%. And the equal amount of fly ash can be replaced. Now this itself is so much of clinker saved, and hence sustainability, moving towards sustainability. So significant amount of work happened, and they realized that Of course, smaller replacement will give you higher strength, but as your replacement increases, there will be some reduction in strength. But at very high, long days, more or less, they will be converging at about 180 days, more or less 50, 60 NPA concretes are quite possible. At 28 days, only at 60%, you get less, but at about 40%, you can easily get about 40 NPA concrete. So they realized that importance and started, using in real structures like, sky trains, etc. way back in 2000. And now we are using in 2020 for various metro construction. But in Western world, in European countries, this and sustainable journey started way back, late 90s or early 2000. Okay, so quite a bit of structures have been built very impressively, and they are still there for you to see. They are all high volume fly ash concrete. So only 250 to 200, maybe 300 kgs of cement has been used for M40 or M50 or M60 grade, which they showed it to the world. And then similar work followed in India also. Quite a bit of works have been done. I'm not going to spend time on that. Parallelly, something also emerged. It was as a requirement because people started looking at workability and a kind of a self-compacting concrete will give you a lot of advantages, because concrete by itself, if you don't vibrate, will give a lot of honeycombs like that. But if you vibrate or don't vibrate, it will get something like this. So that was a good attraction for people to start working on this particular concept of self-compacting on its own. A highly flowable, but it's stable. Can go through the reinforcement on its own, so no vibration required on its own. Consolidate on its own without any segregation. It was a fantastic idea started by Okamura of Japan, and significant work started happening in 2000s, early 2010s. And the finish was fantastic, improved durability, it will reduce noise, and strength also improved significantly. But what was different in this? As per se, the concrete cannot be different, but something which came was using the comparison of a traditional concrete and SCC shown here. More and more powders were the requirement in order for aggregate to be trapped inside a matrix and then carried away, through the flow. We needed a stable matrix. That stable matrix can come only by increasing the fines. Either you can increase the sand or you can increase the fines, and significantly equal amount aggregate can be reduced as compared to the on the left hand side, which we use for almost 150 years. Let us. This was a significant change in terms of mixed proportioning, but that introduced us a more introduction of fines. Fines means again a binder. Now I cannot use a binder of that quantity. When I'm using only 10 to 12%, 18%, it will definitely not sustainable what we are talking about. Again, these wonderful materials came into picture. Okay, so people started using, why can't we blend the whatever available material? It could be fly ash, it could be GGBS, etc. But I have shown only one example here of fly ash, how innovatively one can do. Suppose if I need a 50 MPa concrete, about 430 kgs of cement, but powder is more required for a flow, I would have gone up to 550 kgs of cement, let us say, controlling the cracks, etc. But then I don't do, I restrict here, but then I start introducing more and more fly ash, in fact, as high as 200, etc. With that, the flow started. These are the properties of the same mixes. Let us say slump flow, it was only about nothing when I used only cement, but I started replacing with fly ash, it started increasing, and suddenly I get about 600 flow. Concrete started flowing. So self-compacting concrete was evident by using these mixtures. And in fact, the strengths also, if you look at those mixes, even if I use almost 40-50% of the replacement, you get a significant strength higher than the 48, and at about 270 days, because of the pozzolanic reaction, the strengths increased significantly. So this caught up the world in the last decade, and significant amount of work has also happened in India, and we are moving more and more towards such structures, because imagine the amount of concrete used, and earlier if I using 100 kgs, and now if I'm using only 50 to 60 kgs of clinker or OPC clinker, definitely sustainability is achieved through the route of reduction. quite a bit of such excellent works have been done throughout the world. Akashikaiko Bridge is one of them. More than 240,000 cubic meter of concrete SAC with only 50% of cement was used, and it's functional, opened for public in as early as 1998 and still serving very beautifully, as durable as anybody can imagine. Quite a bit of other works also happened elsewhere in Europe. So pre-engineered buildings, which you're talking about in this ATAL workshop, is something like that actually. So these can be dismantled and reused. So they can be done with this kind of a cement concrete, but at this material. These are some of the other examples which we can definitely use. And fantastic applications have happened. And more importantly, the industrial byproducts have helped to reduce the total binder requirement in terms of only OPC, and that is the change. Now, this is about cement concrete. Now we can start reducing the cement. How much cement we can reduce? Okay, so there is always a limitation. So then came one more radical change. You have seen up to high volume fly ash concrete and SCC, an improved version of high volume concrete, I would say. Then came what is known as geopolymer concrete. I'm likely to deviate now with the cement concrete, but our approach is towards a sustainable concrete. Okay. There is something people now realized that a hard material can also be done by a totally different type of a reaction chemistry. Now we don't need an ordinary Portland cement. We can use only the minerals, let us say, fly ash, industrial waste, and no Portland cement, called what is known as geopolymer concrete. Okay? Now, why it is geo? Geo is materials which are available in the earth can be used, and they can be polymerized to some extent by using what is known as alkalis. Now, the use of alkalis is the only difference. Now, as you can see, Portland basically synthesizes of high calcium minerals, because calcium oxide is about 60 to 70%, for what is known as calcium silicate hydrate gel. And you need water for such a process. This is fundamental. We all know we've been practicing very stable. All that innovation, reduction up to 50 to 60% of PCS happened. If you have to move forward, let us say if you want to get rid of that particular material, use only industrial waste, but I need something to polymerize. So I have silica alumina. I can polymerize through what is known as activation. I will come. This is the only questionable part in this particular technology-wise, achieving the sustainability. But luckily, in this process, water is released during the process, so no curing is required. So I'm saving a lot of water there in terms of that. Okay, so that is something which you should make a note. Now, one or two slides just to introduce you to this new technology. If somebody does not know or used to it, we use a powder basically. Instead of cement, I use something like fly ash or GGBS or metakaolin or rhesus cash. Now, metakaolin, you know that kyanite soil can be burnt about 600 to 700 degrees centigrade, and all those bonds, water is released, and they get a new reactive surface, highly reactive in terms of very high silica and aluminum. Rice husk is an agro waste. After you take out the husk, if you burn again in a controlled temperature, 500 to 600 degrees centigrade, the ash you get has got significant silica. Now, the fundamental principle here is that any material you choose, be it fly ash, GBS, metakaolin, rice husk ash, red mud, or anything you want to use, should have silica or alumina as a precursor. They are definitely required. Then you need activators. The most prominent activators which have come to the fore have been sodium hydroxide and sodium silicate. There are instances, quite a bit of people, Europeans particularly, use potassium hydroxide and potassium silicate. I can also blend a little bit of calcium hydroxide. Obviously, you know from a periodic table, you know only 3 alkalis are there. So all of them can be used. Now, popularly, sodium hydroxide and sodium silicates are the ones which are used. Now, when you mix them, some magic happens, okay? And you get a paste or something which is very similar to your CSH gel. Now, the reactions inside are totally different. This is not hydration. Should not use the word, that's the wrong word. It is polymerization. Now, the type of bondings which happen inside are called silico-oxo-alumino-oxo bonds. They are kind of a network, a 3D network which form. They are very stable. They can also hold on to aggregates and create a matrix. Now, this was something which was realized. Now, mechanism is simple, visualized. The material, whatever fly ash or any material which has got silica, it has to dissolve. Then a gelation has to happen with the alkalis. Then they will reorganize themselves, and then polycondensation happen, which has been conceptualized and shown you here. So any aluminosilicate source has to dissolve into various liquids, and then they have to get that equilibrium, and then gelation will happen, reorganization will happen, okay, and then polymerization will happen, give some kind of a stable form of a network, three-dimensional network. In the process, very important why I've shown this slide is make sure that though initially water is there in the silicate process, because both silicate and sodium hydroxide will have a bound water. We don't have to add water addition, only solutions. But solutions have some amount of, but that water is coming out. Yeah, that's the only significant differentiation. Some reactions I don't expect you to do. You have precursors here, you have alkalis here. Something happens. What is important is silica oxo, alumino oxo bond has happened. What is important is plus H2O. So water is coming out in this particular reaction, which is quite different from the hydration process. Now, something like that, people are showing it. Quite a bit of contribution is evolving over a period of time, and this is there for you to believe that such a structure happens. But physically or microscopically, when you see, which is very similar to our cement hydration, you see fly ash particles, polymerized fly ash particles. When they further polymerize, this is what you get. This is what is silico-oxo, alumino-oxo. This is not calcium silicate hydrated dendritic structure. This is something like that. If you further enlarge it in a transmission microscope, a three-dimensional structure like that is happened. This is your aggregate. And very interestingly, as you can see, this also binds through van der Waals forces to the aggregate. So hence, it can also serve as a binder very similar to your OPC binder. That was the findings earlier. So some work has been done. Many people are working here extensively. We also work in BMS for about 5 to 6 years now. We picked up because they are very popular. Fly ash GGPS now more or less after 15, 20 years, they are coming back. JSW or a few other companies in India give us a nice bags. GGPS. Fly ash, now people started collecting and packing and giving you Dark and Aztec and a few other companies. So we can trust on some amount of consistency of this materials, and hence we have chosen this material. Now, alkalis are very important. Now, I'm sorry, physical properties of this material. Now, these materials, if you grind them, it will become alcofine or ultrafine slag. If I grind fly ash, it will become ultrafine fly ash. So you can have effectively about 4 different types of material to use, play around as a binder. That is important because I would like to draw your attention. The live reactivities vary significantly. More importantly, the glass content or the reactive content becomes very important. It is very good in slag, ultrafine slag and slag, not much in fly ash, and hence always slag is slightly superior in terms of early reaction. Long term, fly ash is equally effective. The other part, so of course, chemical composition of these materials is very important. I would like to, total silica will be here, but what you need to find out henceforth is the reactive. How much is likely to participate in a reaction? That becomes important for you. So obviously, fly ash and GGPS give you significant amount of reactive silicas out of the total silica. In fact, more or less everything available in GGPS is reactive. In fly ash, about 50% is reactive, and hence the quantity which you use in fly ash has a limitation here. Okay, and of course the heat evolved also important. The Fly ash does not evolve much of a heat, but whereas GGBS evolves heat, of course, OPC heat is not. Now in geopolymer, we realized curing is important and some heat is required, and hence some amount of GGBS always helps in geopolymerization. But ideally, only fly ash should be used, but you need additional heat treatment for that. And hence you can use GGBS. But the purist does not want to use calcium oxide because GGBS has got some amount of calcium oxide, which we noted. The only controversial part as of now in most discussions, wherever we go and present it, people agree to disagree, is that these alkalis are sustainable. Because this is a big question. Like cement in the OPC, the amount of material we use, alkalis, could be an issue in terms of bringing down its carbon footprint. The fact that we are not using cement, we are using only byproducts, will add significant credits. And then many people publish it as a green concrete. But there is a contrary argument which is going on, but we can eventually solve that because we have realized that as we go more towards calcium based, the requirement of alkalis is reducing. But somebody wants to explore this in their work. Basically, you need to get hold of the commercial sodium hydroxide, which is available, and commercial sodium silicate, which is available in the market because they are not manufactured product, as you know. They have been used for other purposes, soap and other things. We are trying to adopt it to concrete technology. Some more work needs here in this area. It's a gray area. But a quick pointer for you is to look at this material. It should be, about density should be about 2.1, and look at the various materials available in your sodium oxide. Look at the molar ratio, which is about 1.8. Molarity is about 39 purity. Okay. Then sodium silicate, since it's manufactured with sodium and silica, different people manufacture differently. So ratio between silica to sodium, percentage of silica, percentage of sodium, if you divide, if it is about 2.5. So it can vary between 2 to 3, 3.2. Somewhere about 2.2 to 2.5 is ideal for concrete. Do not go for too much on the other side or lower side. This is some important. This is called modulus, also called modulus of the. Once you identify them, it's easy. These procedures which we use to make such concretes are very simple, very straightforward. Just use the fundamental concepts of concrete technology. Use a particular ratio. Use about total quantity of water, 140, 150 combined water for workability purpose. Use about 25 to 30% of fly ash or any other material, and then add respective quantities of aggregate. So it's possible to proportion it using absolute volume method, which we have been using convention. So one part is done. That is proportioning. Once you have the materials, which are again locally available in most countries, and then you can use these similar equipments also. The same mortar mixer or concrete mixers can be used for mixing, and the same type of measuring equipments can be used to measure your workability, slump, etc. Because it is sodium silicate is there, which is a little bit of sticky, you may not get a quick flow. It will go but very slowly. But one of the beauty of this material, there is no segregation happening. Segregation and bleeding has been a consistent problem for the field engineers to manage. But in this concrete, as a first advantage, you don't have to face any such thing. In fact, you have to solve stickiness the other way. So that gives you a very nice concrete, cohesive concrete, no segregation, bleeding, etc. First step. One. Can you hear me? Am I audible?
Yes, sir. Yes, sir. You're audible, sir.
Okay. Now, curing is something which people worried
sir,
initially.
yes, sir. Very much, sir. Very much. It is proper, sir. It's proper.
Good. So curing of this material was an issue. People looked at it, but initially when we use only fly ash as a binder and then trying to activate demold next day, they used to give away. So started heating up at different temperatures. And we realized that about 50 to 60 degree temperature will give you a nice, initial boost for this polymerization. Generally, polymerization happens at around 50 to 60 degrees in the start. It could be more at a higher temperature, let us say. So that little kick of heat was required. And then the products coming out of that were very, very normal. These are something probably we realized are the craters where water is coming out of such a material. And nice adhesion, we could see van der Waals forces between the silico-oxo, alumino-oxo bonds and the aggregates was also observed. So it gave a lot of confidence. And when you do physical tests on them, there is quite a bit of encouraging result. So they actually followed a similar path as OPC, Abraham's law. You increase the water to fly ash ratio or binder ratio different. GPC also followed the same thing. You increase more and more, solids here or water in the solids. Basically, strength started reducing, increasing. In terms of strength, everything was happening more or less in 3 days only, more or less in 3 days. And after that, by 7 days, it is more or less stuck, and 28 days, hardly any strength, observed. So another great advantage for contractors that, they can use only 3 days of concrete and no curing of water. Look, we are not suggested anywhere curing of water. Great sustainable option for us. Basically, I don't need water. Heat is required. We'll show you how that can also be reduced later. But higher the percentage of binder used, which is fly ash, higher the strength you will get. So as early as about 3 days, one can get about 50 to 60 MPa concrete. It was realized. And Rangan has gone, Curtin University, Professor Rangan, doing this work, particularly has published 2 volumes of work. One can refer them as a primary reference material if somebody is embarking on this area, and has also shown that the modulus, what we come out of geopolymer concrete at different strength ranges as compared to Australia or American codes are slightly less. Modulus is slightly less as compared to the conventional codal provisions. So probably some work is required if you want to use them for the regular construction work. So a point to be noted. That's why I brought this slide here. But what is good is about durability. Now, this is fantastic, particularly some of our work, Dr. Sudarshan worked extensively and under my supervision. Geopolymers, when heated up to about 800 degrees centigrade, okay, and consistently sustained temperature at about 250, 400, 600, etc. For different water to cement ratio. Initially, if you're working between 50 to 70 MPa, at around 250, most of your strength loses. Okay. There onwards, the strength is very gradual. But whatever happens, even at 800 degrees centigrade, you still have a significant residual strength, 20 to about nearly 35 MPa, which is good enough as a safety net for, in fire accidents. And in fact, when we took out these samples out of the furnace, it could be handled very easily, and they were red hot like that. And the microstructure still shows, even though there is some dryness which happened, it is well intact. Compared to your cement concrete, it would have crumbled at around 450 to 500 degrees centigrade. You don't get anything much out of in OPC. And it's definitely a temperature resistance material as of now. The other outstanding feature of this particular material in terms of its durability is when you put it in acids, the OPC more or less deteriorated, whereas GPC, geopolymer concrete, did not even show any distress at even 4% of a solution of H2SO4, even at almost 3 to 6 months. So this shows that we can straight away use this material in most of the waste plant treatment or sewage treatment plants, or which can hold a lot of chemical structures, basically, and holding structures straight away. No code is required, it seems. So wonderful material as well. Sulfate resistance was very consistent. No unusual reactions are happening. So with this, it is established that it is could be an alternative to cement concrete. one can explore, because similar mix procedure, comparable short-term, long-term properties, drying shrinkage, I did not show here result, but hardly shrinks basically this material. And good chemical attack resistance is shown. So good in basically aggressive environment. Now that was with only fly ash, but for a country like India, which has got significant amount of heat for almost 8 to 9 months in a year, we thought, is there some more innovation possible? Yes, it is possible, because we know, we have shown this, heat of hydration is slightly more in GGBS as compared. And hence I was using a heat, early heating for curing purpose. What if I incorporate some amount of GGBS? Now such concrete does not require elevated temperature curing, but also water curing will be a promising alternative to tropical countries like India, wherein we have about 25. But the purists may not agree with this, European, etc. No, you cannot introduce a calcium media into a geopolymerized media and etc. But it's not, hybrid systems have always existed in nature, and why don't we try, as long as their durability is satisfied? Again, durability is a relative term. Durable for 50 years, durable for 100 years. Again, is a question. If people can solve that problem, why not? So some amount of work was taken up and started replacing with GGBS, this fly ash. Okay. So as you replace with GGBS, as I said, GGBS is a much better cementitious pozzolana. The strength started always increasing. So there is no, obviously 100% GGBS will give you a fantastic strength. But one of the problems we realized was the setting time was also very high. You hardly get any time when you go beyond about 40 to 50% of GGBS replacement with fly ash. There was a danger at one point of time that the material actually set immediately and the mixer itself will go, damaged so fast. Probably one can use it for a repair material, such material. So some work was done. No curing, elevated curing, just in a shade or like any of your structures, or put into the real-time testing, sunshade, shade, and directly. If you put it directly on sun, some amount of cracks were observed. Basically, finer material was used, but otherwise seems to work if you just moist it just for the purpose of shrinkage purpose. So even the hydration, when you looked at microscopically, so polymerization is happening with the fly ash particle, and GGBS, of course, are random particles. So calcium, silico-oxo, alumino-oxo, and calcium hydroxide crystals could be observed some places, and ettringite, like your calcium silicate hydride, etc. So CHS. So it was a perfect hybrid, coexistent matrix was observed, and not much of a deterioration was also. So calcium hydroxide crystals one can observe here. So there is a calcium silicate hydride and there is a silico-oxo alumino hydrate bonding coexisted in this particular system. So we believe significant work is happening in this area, and subsequent amount of geopolymer work is always with some amount of GGBS. Maybe reduce a bit just to kick off that polymerization we use as an activator, further activator, and subsequently use more and more fly ash. Quite a bit of structural work has happened in many places. Beams and columns have been cast and they have been tested for their flexural work. More and more structural engineering students can take up this kind of a behavioral performance of these structural elements, different elements. Some work is there, but in a 2-point load, flexural loads, there was not much of a difference. Beams cracked very similar to your cement concrete beams. There was no sudden failure or something unusual behavior was observed, and hence we can believe that this technology can work. Australia started picking up very quickly this technology, started pre-engineered elements like box culverts. First they started using in roads, nothing can happen. So any streams, etc. in forest area where you need to build a quick roads, you put these box culverts to create a cross drainage work, and continue your roads in a very remote area. So geopolymer, durable material, sustainable material, because there sodium silicate, sodium hydroxide are very, very economical there in Australia, but here we are spending a lot of money, needs to work. So quite a bit of work picked up. As of now, people started looking at M40 grade of concrete. And in fact, one of the first 100% sustainable construction, just to show sustainable construction, called Global Change Institute was built using M40 grade concrete. All of them are geopolymer, pre-engineered elements which have been assembled here to build a house. So it was taken up as a pilot project. Many people have started using footbridges initially, if you are not very good at promoting buildings, which most of the time mental block will be there in many countries, particularly in developing countries. You can always start with infrastructure projects, small footbridges, or maybe roads, sustainable roads, jetties, where you need access to people, or on the basement or base, subways can be built for pre-engineered roads, for example. That people have started using pavement concrete. So significant work is going on already, and few innovative entrepreneurs are coming up with such a mix, silica, fly ash, etc., and then separate activators, and they have started promoting them as a pre-engineered material or pre-engineered concrete structures. So quite a bit of work is done elsewhere, but we are yet to catch up here. But something which can start now, probably some manufacturers are already thinking, is the geopolymer RMC, ready-mix concrete. Now, once this comes, probably the real issues of using the alkalis and some engineering inputs required can be solved here for the user. One can do that. And quite a bit of precast elements have started coming, which are beautifully done, as good as any one of those UPs. But please remember, no OPC here. Okay. So there are a few challenges in this particular route. The role of water is not yet understood completely, so we need to dig deeper. So some researchers who are willing, they can do it. Sodium silicate customization for construction is required, because what we get now in the laboratory is not made for construction, concrete. It is made for something else. So we are getting what they are generally manufacturing. So quite a bit of innovation can happen there. Flexural performance or even modulus, which Professor Rangan has shown, is an issue. Seems slightly lower values with the existing codal formulae which have been given. So maybe we have to modify the formula itself to get that, or improve flexural performance using fibers and things like that. Because we use alkalis, safety issues will always be there if you want to use it in site. Now, this is something replacing a binder produced. Now, if you look at concrete, one is binder, another is aggregate. Now, aggregate also we are struggling using natural resources, and then even the manufactured aggregate, which is called crushed stone sand, is again is quarried and then crushed. A lot of energy is involved. So one of the thinking for us was, where can we further embark on using some more industrial waste to reduce the important industrial waste, let us say fly ash. Now many cement companies are using composite cement, is happening, but if it is happening 100%, then there is no fly ash. Is there any other alternative for us? So work has to continue. One of the options which we found was the red mud. So amount of red muds are available in most of the aluminium plants. One of them is near Belgaum. This material is a very attractive, wonderful material. Looks something like that, brick red color, and chemically it consists of silica, alumina, iron oxide, etc. Very, very similar. But make a note, not much of silica, but more of iron oxide, and then more of alkalis. And hence it also showed a high pH. Now that is something which we were interested to use in geopolymer, because I need a higher pH, I need alkali, whether I'm getting a natural alkali here. We wanted to investigate that. So some work has been done here. So XRD showed and SEM showed that these are all lumped because of the disposal process. Small red mud particles have lumped together. One idea is that you can make a small grinding, but then energy is used. But even simple grinding can help. But even otherwise, they are much, fine material. So an attempt was made to use them at different percentages. Fly ash itself was replaced. And it appears that at 100%, we don't get much of a reaction because red mud, not much of silica is there, but only iron oxide is there. How much reactive iron is a question there. So, but there is some amount of reaction is definitely happening. But as you use more of fly ash and less of red mud, at around 30%, okay, so 40 to 30%, 25 to 45, if you want to put a range for that, you see significant strength increase. So further fly ash can be reduced in terms of preparing a geopolymer. The microscopic study showed significantly that at M30, you get a significant amount of geopolymerization, calcium silicate hydrate. But as your red mud incorporation increases, hardly any reaction happens at higher percentages. Probably it is the property of the red mud itself. But something interesting we also dwelled upon. Davidovitz said this material is highly durable because it has a ferrosalite. Ferrous, as you know, iron is one of the very strong component basically. So when silico-oxo, alumino-oxo compounds are there, apart from your silico-oxo, alumino-oxo, you get a ferrolink. Now this ferrolink is very highly durable, and hence makes sense for people to use this material. And we also looked at internationally and our work basically. Dr. Smita worked on this, defended her thesis a year back. About 15 to 16% of ferrous in one of the form, F2O3, there are 7 to 8 forms there. One of the form can be very significant participant in enhancing the properties of geopolymer concrete if you are looking at enhancing your already existing geopolymer properties. That much I can say. So quite a bit of work is done. I'm not positive of sound. I'm not going deeper. One more last thing before I end was something which is close to my heart, as I did some significant work way back in 1990s. But now we found a renewed interest. As we realized that this pond ash, as thermal power plants are increasing day by day, more and more pond ash. This is a site of a Ballari thermal power plant, which is a very recent one. And if you go to 90 and odd power plants throughout India, major power plants, you will get such hundreds and hundreds of acres of land filled with this kind of a material. Not many people are using it. Some people are using it for backfilling and here and there some bricks, low quality bricks, etc. Not much of work is done. Now we looked at is beneficiation possible for this to be used and replace the other part of it or the main part of it, let us say. Quite a bit of interest has come in last 1 or 2 years. That because about 1.5 billion tons of pond ash is estimated in India. And in our own Karnataka, if you see, almost about 50 million tons is available if you go about 200 to 300 kilometers from Bangalore. Now that's quite a bit of material, ponded material, which can be beneficiated and used. So we looked at it further. Sustainability, can it be brought? So, but pond ash, when it is arts collected state, most of the material, 100% of material is only 300 micron and below, not much below about 20 micron, etc. So some amount of grinding was done using a pug mill can be done. So unprocessed pond ash, UPA, and it can be ground into different grade A, grade B or something like that. You can do that. We have tried. So unprocessed pond ash is a lumped particle like that because fly ash with bottom ash, everything is mixed in water and dumped here. After 3 years, 4 years, if we take out, this is what you get as a material. When you see it in an XRD microscope, this is about 10 micron. That's the size. Now, when I grind it, all this is broken and then they become a little more reactive. It was quite interesting. It's a recent work happening with one of my PhD students, the other. So we realized that this material, when you would grind it, can be used as a binder itself in a geopolymer concrete. Unprocessed can be used as a fine aggregate, which means effectively the same material dumped, not used at all, can be used to prepare geopolymer concrete. So fresh 2 years, 6 years reactive silica, as you can see, there is some amount of reactive silica. Otherwise, you get same amount of calcium oxide, and loss on ignition was under control, less than 6%. Now, when we found out lime reactivity at about 10 days or about 28 days, but 10 days is what IS 1727 prescribes you. If we don't do anything, it's only less than 1, but if you grind it, it will increase. So 2 years, 6 years, these are all different type of depth at different depth and different bonding agencies we are looking at it. So suddenly there could be some life in this particular unreactive material if you go for a mechanical activation or a mechanical grinding, we realized. And then of course lime reactivity started improving, and using such materials we prepared a simple process wherein we replaced only fly ash with ground pond ash at various replacement, one set, and then we kept this particular ground pond ash 100%, okay, and then replaced only fine aggregate, for example. All aggregate was kept constant and only ground pond ash was used. Here only sand was replaced. Basically earlier pond ash was used as a sand. Here pond ash is kept constant, and then ground pond ash was replaced with fly ash. In effect, 100 GPa means you have 100% of ground pond ash and 100% of pond ash as a fine aggregate. Here 0 EPA means you have 100% of fly ash and manufactured sand. That is the meaning of it. Look at the results before I conclude. This material showed significant, let us say if I take it as a purple, 28 days, not higher sun, about 50-55 MPa concrete was there. And then I started replacing with fine aggregate. This keeps reducing as you replace with your manufactured sand, but not significantly because your fly ash is giving you most of this one. But after 0 MPa, that is that your material, when I started replacing fly ash itself, the strength reduces basically, but still holds on to around 40 MPa, which means the ground pond ash with about 2 to 3 MPa ram reactivity and 100% of pond ash can be used to prepare a concrete. And this is wonderful because it is all about reduce and reuse concept. Second part of it, which somebody is talking about in future, let us say. So very entertaining, but the embodied energies calculations are going on. But we are certain that this will give you some a good ray of hope. But the only part here is that the alkalis are going to bring that energy. So how that can be reduced is the next challenge, for example. Another interesting thing we looked at is what the densities of such concretes if used with any of those industrial material can be significantly less. Imagine from 2,300 to you are bringing it to about 2,000. So imagine if you are building going forward about 25, 50, 75 stories of building, any amount of, even if they are walling elements, infill walls basically, the amount of reduction in weight and hence reduction in foundation and the material usage can be humongous sustainability in terms of using amount of concrete. So that's the hope we have. So this is a work in progress, I would say. Significant efforts can be done. Different people can think differently for bringing in sustainability. What I have not talked about is the use of water and other sand replacement techniques, which people are doing it. They are most welcome to do it. We looked at one of the alternative, but as of now, geopolymer is not necessarily the alternative. So in conclusion, development in the field of concrete technology are far-reaching. We realized paradigm shifts in concrete concepts are evident to move towards sustainability, starting from introduction of this mineral addiction. It is no consultant will touch fly ash. Even in Bangalore, when I came in 90s, late 90s. So in 1999, I came to BMS. Many of the leading consultants here were scared of using fly ash in any form, including composite cement. So from there, he now towards 50-60% of replacement, the amount of concrete jingle we have created in Bangalore, definitely some 20-30% of savings has definitely happened. So we are moving towards sustainability. Definitely more work is required. Geopolymer can definitely serve one of the greener concrete for sustainable development. But I would like to put a word of caution, but by no means it is yet an alternative to cement now. Cement remains to be most popular and continue to work for a few more years unless we come out with a foolproof technology. Thank you very much for your kind attention. I hope I have done justice to the topic on towards sustainable concrete. There are many innovations possible. Thank you very much for the opportunity. I'll stop here for any questions here.
Thank you so much, sir, for your wonderful presentation. Dear participants, sir is open for questions. If you have any questions, please type it in the chat box and I'll just read it out to sir. Participants, if you have any questions, please type it in the chat box. Sir, there is one question from Dr. Jyoti.
Okay.
Ma'am wants to know the recent research on pond ash, which you have mentioned in your presentations. Are you using alkaline solutions, sir?
Yes. Yes, I'm using alkaline solutions. Sodium hydroxide, sodium silicate. Can you see this?
Yes, sir. Yes, sir.
As of now, I have used about 10 molar solution, but that is more we can, because we have realized that if you bring in more and more calcium oxide related materials, the requirement of sodium goes down.
There is one more question from Professor Arjun. Sir wants to know, can alkali activation be possible for non-pozzolanic wastes which are as fine as cement or fly ash?
No, see, that's what I kept on emphasizing. The first thing is to realize that there are active silica or alumina or iron oxide. Unless they participate in activation, if they cannot be dissolved for dissolution and for reorganization, no alkali activation can happen, no polymerization can happen. So, for example, to answer his question, if I take a sand is a crystal basically. If I keep grinding and grinding and grinding for some amount, to some extent, some amount of amorphousness can creep in, but it is only to that level. Otherwise, it cannot never replace. Once I grind it to about 20 micron equivalent to cement, it will act like a cement. That is not going to happen. Yeah.
Thank you, sir. I think that answered Arjun sir's questions. Sorry, somebody is speaking.
Girish sir, Sridhar here. Am I audible?
Yes, sir. Sridhar, sir. Yes, sir.
Okay, sir. I have a question to sir. Good morning, sir.
Good morning. Good morning.
Sir, just thank you so much for actually giving so much of actually advancement in production of concrete as a sustainable material. Wherein once, sir, C.S. Vishwanatha, sir, that is, he is not there now. It's worth remembering him on this day. So once, maybe 20, 25 years back, it's 20 years back, it seems, when I heard him in a conference, he was talking about this geopolymer concrete, wherein this is in future going to actually replace the conventional OPC concrete, and we may go up to 200 MPa of concrete. We can go up to a strength of 200 MPa without using water for curing. So here, as I heard you, we are actually at around 40 MPa now. 40 to 45 or 50 MPa. If we go up in this actually strength ladder, what changes we can actually use to make to get high strength concrete, sir?
Yeah, okay. Thank you for reminding our mentor, process CSV, the mentor for many of the engineers, even at our age. How many people, Professor Jagdi, Dr. Kalgal, everybody acknowledges him as a mentor. It's not 20 years, it's about 10 to 12 years, 2008-9. First time he spoke about geopolymer concrete. In fact, that is the start point for our research. Okay. It is possible to reach strength. Whatever efforts we have shown here are not towards strength enhancement, but they are more towards sustainability. But cut off all the sustainability part, use the very highly reactive fly ash, very good GGPS, incorporate few more silica-based precursors like microsilica or nanosilica or few other metakaolin. You can hit up to 120, 130. People have already reported. There is nothing great about achieving a strength even in geopolymer. That's possible. 200,
Thank
I
you.
don't yet, because then you have to cut down the aggregate. The aggregate, if you have more than 8 mm or 10 mm aggregate, you're not going to get 200. That's a reactive product concept. You have to reduce that van der Waals forces. So aggregate has to be knocked off in your system.
Thank you, sir. Thank you so much.
Answer your question. Any other questions?
Thank you so much, sir. I think that's all the questions that time will permit us. If there are any further questions, we'll have your mail ID so that. I think, sir, one last question. Of course, your Vishwanath sir.
Somebody is asking a
Yeah,
question.
I'll just read it
Yeah.
out. What made Vishwanath sir wants to know what made you say regular cement would stay in. Sir, Vishwanath sir, I think I'm not able to get a question here. What made you to say that cement would stay in spite of GPC showing all qualities required by a structure?
Oh, that's by sheer volume. By sheer volume of concrete, which is needed some 15 giga tons throughout the world. The available industrial weights cannot match that kind of a volume. And hence,
GPC, geopolymer, showing all
volume, sheer volume.
by texture.
So much of industrial weights are not yet available. That's the only thing. And then we are not yet ready as of activators are concerned, how much they require. We are not yet reached an optimal value where we need so much of activators, and then whether we have a resources. Recalculation has to be done. And hence I said, as of now, it is still on only a small alternate. Cannot be a complete replacement to cement. Can be one of the alternative at many places, in fact, not one or two, which people are exploring already. Quite a few roads are being built. Sewage treatment plants are being taken up by subsequent governments. But slowly it will start. But it did not progress in the speed at which we wanted it because of the limitations of the alkalis. Another researcher, Dr. N.P. Rajamane, has done quite significant work in this area. He has a tall claims at times, but we don't know how much it appears. Claims are more than what can be calculated. That's the limitations of this technology as well. That's why I said, but it's very promising.
Thank you so much, sir. I believe there are quite a few more questions, but as far as the time is concerned, we will have to restrict the questions to this point. And thank you for your wonderful presentation. I request Head of the Department of Civil Engineering, Dr. K.N. Vishwanath, to kindly conclude on the session.
Thank you, Girish. Raghunath sir, it was a very, very eye-opening session. As usual, we keep looking for your lectures. It's always interesting to hear from your end. Sir, starting from sustainability, you went on to say, we went on to the concrete and we said the concrete is not that sustainable and it has to be made sustainable. We call it as green concrete. And what are the constraints to be made a concrete to be green? And then you went on to say to make it green, we need binders. And then different types of binders were shown and explained to us. Then their properties in contributing towards the strength, the durability, resistance to environment, and all the things were explained by you. Then a sort of journey of concrete also you said, from OPC to PPC, and then blended cement, and then HVCE, HVFA, high volume fly ash concrete, and then finally you touched upon geopolymer concrete. Then what are the properties of geopolymer concrete, like no segregation, and it is resistance to fire, and then it has good acid resistance. With geopolymer, we are using no cement, and hence this is an answer for sustainable and eco-friendly concrete. That was the answer given by you, sir. Sir, it was a very nice presentation. You took us through the stages, how the concrete has been evolved towards sustainable. It is very apt to the topic that you had shown in the very beginning of the slide. Sir, as usual, it was very nice and informative. So we wholeheartedly thank on behalf of DSATM, our college management and our principal, as well as from the faculty and students of Department of Civil Engineering, and from the participants end for this very informative session. So thank you for the time you have spared and the knowledge you have shared with us. Always very eager to listen to you. And of course, we have also grown looking at you and seeing you. We have learned many things from your end. You're an inspiration to all of us, sir. So thank you. Thanks for your time and knowledge. Thank you so much.
Thank you. Keep continuing the good work. Congratulations for this particular workshop.
Thank you, sir.
Shares knowledge to various people who can learn. Speakers are very impressive. Professor
Yes, sir.
Jagdish, for 2 sessions itself is you're most lucky.
Thank you, sir.
Okay.
Thank you, sir.
Congratulations.
Thank you,
Keep
sir.
doing such good work. Okay.
Yes, sir.
Best wishes.
Yes, sir.
Bye-bye.
Thank you, sir. Thank you. We need your support and guidance.
Sure.
Thank you, sir. Over to Girish, Professor Girish.
Thank you so much, sir. Rangnath, sir, thank you so much. It's always a pleasure to listen to you. Even though faculty members we are, but listening to you, we feel going back and sitting in your class and listening to your lectures like small kids. Thank you so much, sir. Subalakshmi ma'am, would you can
Thank
you
you for the
conclude our
host and thank you for the host, Dr. Shubhalakshmi, for coordinating.
Thank you, sir.
Excellent.
Yes, sir.
Thank you, sir.
Thank you, sir.
Subalakshmi
It's
ma'am.
our
Yes.
Madhu here, sir. Rangnath, sir, thank you so much. So,
Thank
we
you.
are-
Thank you. I acknowledge all the necessary preparations. Thank you.
Thank you, sir. We are going to wind up this session now, and next session will be by Dr. K.S. Jagdish, sir. There is little changes in the schedule at the last minute of the day. So now next session will be by Dr. K.S. Jagdish, sir, at 11:45, and afternoon we'll be having the session by Dr. P.S. Ramesh, sir. So we'll take a break now. We'll join back at 11:45. Thank you.
Thank you, ma'am. So, dear participants, we'll take a small break of about 15 minutes and we'll meet back in the same link at around 11:45. Thank you all.
Dear participants, the next one is an interesting session by Jagdish, sir.